Yeah, welcome to my talk. I will be, as Christoph already introduced, talk about brain stimulation and optimizing open loop and closed loop brain stimulation procedures. So my talk will be divided into three large blocks. First of all, I will talk about brain stimulation in general, principles and practice, the clinical approaches and clinical research approaches. Then I will head over to hardware and software solutions for advanced neuromodulation, so how we can evolve from the standard clinical procedures into more the research perspective. And then I will finish with a few examples and give a live demo. And I hear I have kind of an echo. Maybe someone is not muted. Okay, now it's better. Thanks. Good. So brain stimulation. It was a question before. Of course, we're talking about invasive brain stimulation. So it's always about implanting electrodes and directly stimulating the cortical tissue, either at the bedside or during surgery. So why do we need brain stimulation at all? Christoph has already introduced you a little bit to brain stimulation, but let me summarize it again. So one very big block in the clinical domain is the identification of brain functions. So this includes electrical cortical stimulation, or ECS, cortical evoked potentials, or CSEPs, somatosensory evoked potentials, or SEP. So these are mainly the three big application fields for functional brain mapping. The second very large category is the treatment of disorders, also clinically used, especially for treating patients who are suffering from the Parkinson disease or essential tremor via deep brain stimulation, or the treatment of epilepsy via vagus nerve stimulation or responsive neurostimulation. So out of those six application fields, kind of the research scenario arises. And I have summarized it as open loop and closed loop neuromodulation for clinical research. So open loop basically means that we don't have any feedback from the system. We are just, stimulating a brain region and observing what's happening. And closed loop means, and it's actually much more sophisticated, it means that we are using feedback from the system, for example, via recordings, ECoG recordings, and the like. So having this overview, I'm going to go through the application scenarios now step by step, starting with electrical cortical stimulation as the probably most famous representative. So how does it work? So we are injecting electrical current into the brain, and thereby we are overriding the electrophysiological activity, which means we can either excite a particular function. So the typical protocol you can see here on the right. In the beginning, we are in the resting state. The patient is just, relaxed and not doing anything at all. And then we're stimulating a particular cortical region. And depending which function is associated with this region, we have functional behavioral response. For example, the hand is moving, or there is some visual illusion, or some sensory, some sensation. And this is reported by the patient and observed by the doctor, and then used for interpreting the functional map of the cortex. The second approach is we can inhibit a particular function or suppress it. So this protocol means that we are starting with a standard behavioral task, for example, speaking, and then we are stimulating into a region where we believe it is involved in or it is necessary for speaking. And if during stimulation the speaking stops, then we know we have hit this target area. So this is inhibition. So using these two approaches, we are able to step by step establish a functional map of the cortex. And just as a remark, ECS is the clinical standard for doing functional mapping since almost 100 years or 90 years. And it's extremely important in surgery planning and evaluation. And it can be done, as I already said, either during operation, so you maybe wake up the patient during surgery with the open skull, or you don't even have to wake him or her up, and you can do ECS, or you do it with implanted electrodes, meaning that first you implant the electrodes, then you have 1 or 2 weeks, the patient is in the hospital, and then you can do bedside ECS sessions. So yes, how does it fit into the overall functional brain mapping approaches? There are actually three kinds of how we can do brain mapping. One thing is we can observe the brain. We can see what brain regions are involved in carrying out a specific task. So this means that we use imaging procedures largely for this approach. For example, fMRI, which is very famous, or ECoG or EEG, or other techniques. So here we can only tell which brain area is involved in carrying out the task. A little bit more specific is the testing for the necessity of a cortical region. So this would relate to the suppression or the inhibition I talked about at the previous slide. So we can test whether a brain region is necessary for carrying out a task. And here only ECS or TMS or the water test are possible modalities to do that. The third one is we can test for sufficiency, which can also be done by ECS. So here we can see whether one particular region we are, for example, stimulating is sufficient to carry out the task, which is the typical excitation protocol from the previous slide. So here we can use ECS or also TMS for this. So TMS is a non-invasive technique. It's called transcranial magnetic stimulation, where you're stimulating the brain via a very strong magnetic field. So what can we map? Probably most importantly, or most obviously, we can map motor function. So we can, via stimulating, induce involuntary motor responses. And the good thing about this is we don't even need the patient to be awake. So this can be even done under general anesthesia. Secondly, we can map somatosensory functions. So when we stimulate the sensory cortex, then the patients usually report strange feelings or numbness at their palm or hands, fingers, whatever region we are hitting. So yeah, this is how we can map sensory functions. And third, and probably the most advanced category, are cognitive functions. So spontaneous speech generation, picture naming, comprehension, calculation tasks are also possible up to a certain degree to be mapped. And all of these are like the cortex, the cortical regions, which are responsible for carrying out all these very important functions is called the eloquent cortex. So this is a very general term in functional mapping. Good. So now let me give you a brief example how ECS works. So here we have a patient. You can see a brain from a co-registered MRI and CT scan with the electrodes indicated here. So this is the left hemisphere. You can see on the frontal lobe and on the temporal lobe, we have two standard, I think, 20 channel grids implanted. You can also see the larger distancing. So these are just the standard grids of probably 1 centimeter electrode to electrode distance. And here on the motor cortex, we have a high density grid. So here the electrodes are a bit smaller and the density is much higher. So when we start, this was done in, interesting. This is the first time that videos are not working. Okay, let me start the presentation again. Maybe I can start it from here. Cannot play media. Okay, anyhow, I will. So this example would give you the patient view, how he is moving the hand, and once Dr. Kamada is stimulating into the hand motor region with 4 milliamps, he's not able to move anymore the hand. So this is kind of the inhibition example where we are suppressing brain function. All right. So a little bit from the engineering side, the technical aspects and procedure of ECS is that we have typically a rectangular pulse shape, which is alternating, so biphasic, so to speak. It has a positive and a negative lobe. And we have a duration of these pulses of 300 to 500 microseconds. And the current is usually between 2 and 15 milliamps. The pulse rate, so the pulses are delivered at the rate of 50 to 60 hertz, depending on the protocol. And usually we stimulate between 2 and 5 seconds. In the beginning, we start with very low current, where usually the patient has not any symptoms, and then gradually we increase the stimulation current until we observe some symptoms. So it should always be as comfortable as possible for the patient, and of course it should not cause any pain or any other inconvenient symptoms. So once we have reached a level where we can observe symptoms, we observe the symptoms, we report the symptoms, and the doctor is taking notes, and we are changing the stimulation sites as we need it. But it can happen that patients feel pain, or also called after discharges happen. So this means that, especially for epilepsy patients, stimulation can cause some pathological circuits to be triggered, and this can be very dangerous because it can lead to epileptic seizures. So in this case, either the settings are we are going down with the current again, or we are keeping the settings and going to another location, or we are even stopping the mapping. Okay, it's really a pity. Seems like the videos are not working, but please just give me, maybe Christoph, you can answer one question and I can fix this. I just play the raw videos and then it should be fine.
Sure. So one visitor without the name is asking, can we repeat the same ECoG experiment by using the EEG recording and get almost the same results? No, that's not possible because the EEG spatial resolution is much worse than the ECoG resolution. Just because all the scalp, the tissues, and the fluids are in between. But we can use the ECoG experiments to get a lot of inspiration where cortical centers and functions are located, so that we can try to put the EEG electrodes over these regions and use them for certain applications. So if we do the brain-computer interface stroke rehabilitation, we want to capture, for example, if a stroke patient is matching left or right hand movement. And then the brain-computer interface with the EEG signal can recognize that the person is now matching left-hand movement, and we can switch on an electrical stimulation of the left hand. And for that, the EEG resolution is just good enough. And if we want to identify another motor function, we can use the ECoG, for example, to find the leg region. And then we know where we should put the electrodes in the EEG recordings to get it. And please, Johannes, just go ahead.
All right. Yeah, apparently I just had to close PowerPoint and start again. So now it's working. This gives you a very important example because it's kind of summarizes all the important findings. Sorry, can you turn off your microphone, please? So Christoph is sitting next to me, and this is why I sometimes hear my echo. So this gives you a very important example of what can happen with ECS and kind of the takeaways and the most important aspects we have to consider. So this patient here, you can see here in the blurred video, he's undergoing an ECS mapping. You can see Dr. Kamada here. And he is in conversation with Dr. Kamada, and we are stimulating into his mouth area. And we want to check whether this is functionally, this is the area we are stimulating is functional or not. And what happens here is, so here they're talking, and then the stimulation artifacts can be seen here on the ECoG. So we are recording at the same time as we are stimulating, which is very important, as you will see in a minute. And this patient somehow didn't really respond behaviorally to ECS. So we had to increase the current, and we had to make the stimulation sequence much longer. As you can see here, it's far longer than recommended. And here, if you look at these channels, you can see that these so-called after discharges are occurring after the stimulation. So this is, as I already said, a kind of pathological circuit in the brain, which is triggered by electrical stimulation, and they can diminish after maybe 20 seconds or a minute, or they can evolve into a generalized seizure. And unfortunately, the second case was true here. So at this moment, the patient was not able to respond anymore, and you can tell from his movement that he's going into an epileptic seizure at this very moment. And at the very same time, you can see that the brain waves are really going wild. So ECS is of course extremely beneficial for clinical purposes, but there is always the risk, especially when treating epilepsy patients, that you run into a seizure. And I was there. I was actually recording the video and the brain waves at the very same time. And believe me, for me as an engineer, it was a terrifying moment, especially when you see here not only the patient, he looks very pale and in a very bad shape, but when I advance a little bit, you can see how the brain, how the brain waves should look normally, but after the largest portion of the seizure was over, and if you look at I just scroll a little bit to here, to this part, and when you see kind of these brain waves, you really know that something is terribly wrong. So obviously, this patient, I mean, the doctors, they reacted very fast, and they gave him some anti-anesthetic, anti-epileptic drug immediately. So it was possible to really contain the seizure, but of course the patient had to rest at least 1 or 2 days afterwards, and we couldn't even think about continuing ECS mapping. So yeah, the video takes a little bit longer. So you can see here that gradually the brain waves are kind of the very low, the rudimentary brain functions come back. You can see this by this very low brain waves. However, the patient was unconscious at this moment and just put to rest. So from this example, we have kind of 4 important takeaways. So first of all, you can see we are recording at the same time as we are stimulating. So it's extremely important to monitor the brain during an ECS session, not only to observe the after discharges and to make sure that once an after discharge occurs, to wait until it has diminished, because stimulating into an after discharge with typical ECS settings can be even more provocative in terms of eliciting seizures. And then you always have to take care when you're stimulating, because you can elicit seizures. And so this is maybe the second point. And the third point is, I mean, this is an example where the patient had a seizure, but you can imagine that each stimulation site you're investigating, it takes at least 2 minutes to do an ECS mapping for that, but maybe it's 5 minutes or even 10 minutes, depending on how much you have to play around with the settings. So it takes really long time, ECS. And this is also the reason why usually ECS is not completed for the whole cortex, due to safety reasons, due to the time duration, and even if you're not exploring the whole cortex, usually ECS takes several hours or even 1 or 2 days, depending on how in which shape the patient is. And this is also the reason why when you're doing ECS, actually the majority of the cortex issues usually remains unexplored. So these 4 points basically summarize ECS quite well. There has been a very valuable review about ECS benefits and also a little bit about the drawbacks. So a very big meta-study about published by Hammer and colleagues investigated the deficits, the post-surgical deficits, depending on whether ECS was performed or not prior to the surgery. And it turned out that with ECS mapping, the post-operative deficits were decreased from 8.3 to 3.4 seconds. The gross total resections, which is basically kind of the amount of tumor you have removed, for tumor patients, it increased from 58 to roughly 75% due to ECS. So this is also very beneficial and a good outcome. And as you have seen from that on the previous video, also here, 3 out of 90 studies reported patient seizures during ECS, and 2 out of 90 studies reported language deficits after resection. So this kind of gives you an idea why ECS is still the clinical standard. So we have talked a little bit about stimulating and recording at the very same time. So when you're doing bedside ECS, usually you're stimulating via your ECoG grids and you're at the same time recording via the ECoG grids. So here you can see a head box from our company, g.TEC, and it seems quite okay to plug in and plug out some electrodes you want to stimulate. But usually these are recorded are connected to the amplifier, and in reality it looks like this. So when you have recorded 64 electrodes to the head box, it's really, really painful and tedious to go back and forth with the simulation electrodes. So one solution to that would be to change from manually changing the electrodes to digitally doing it. And this is why we have developed a programmable switching unit, which we are actually quite excited about, and I will dedicate a few slides on that later on. Good. So, I mean, this was quite a large part about ECS because it's so important, but there are also other brain mapping stimulation procedures, for example, CSEPs. Christoph has, I think, also talked a little bit about this. So here with CSEPs, we can reveal physiological and also pathological cortical networks. So we can stimulate into a cortical location. For example, here in this example, we stimulate into the area indicated by the red dots. It's the Broca's area. It's responsible for generating speech, and we're stimulating with very short pulses, 300 microseconds at 1 hertz, and an amplitude of 5 to 15 milliamps. And we can record the evoked potentials. So every time we are stimulating, we are recording a little fragment at all the other cortical locations, and we are averaging these curves. And then in the end, we investigate these so-called evoked potentials. And here you can see that on the in the motor area here, this grid is placed on the motor area, we can see a very pronounced CSEP, cortical evoked potential, at the mouth motor area. So with this procedure, we have actually identified the part of the language network. And also on the temporal lobe, we can see evoked potentials at Wernicke area, which is kind of the receptive language area. So this is actually quite impressive, because just with one stimulation protocol, with one stimulation experiment, we have revealed the whole language network of the patient. And the very good thing here is also that the patient usually has no sensation at all, so it's just passive. Okay, and then also very important, especially during surgery, is somatosensory evoked potentials, SEP. What we can do here is we can reveal the functional border between primary motor and somatosensory cortex, which is also known as the central sulcus. And when we are stimulating the median nerve here, so right at the wrist, with a frequency of 0.4 to 2 hertz, 500 microseconds pulse width, and 1 to 17 milliamps, depending on whether we are stimming invasively or not invasively. We can also record the evoked potentials on the cortex. And what you can see here, and for me it's always very impressive to see that, we can see that the evoked potential has a phase shift across the central sulcus. So here you can see that the positive peak comes first, and also here, but when we're going over crossing the central sulcus, the negative peak comes first. So this is very important during surgery when the surgeons wants to locate or wants to optimally place a grid. They are placing it over the whole sensory and motor cortex, then they're doing SEP, and then they know where the central sulcus is approximately, and then they can still adjust the position of the grid. So this is very, very convenient. All right, so let's head over to the stimulation protocols for treatment of disorders. So maybe most famously, and we also have a very good talk afterwards by Nuri, it's DBS, deep brain stimulation, especially for treatment of movement disorders, for example, Parkinson's disease, essential tremor, or dystonia. Maybe most importantly at this high level is that in the standard version, the subthalamic nucleus is stimulated all the time. So this is the region which kind of is responsible for this tremor and for this movement disorder. However, it has been shown that this stimulation can also be done adaptive. So here we are coming from an open loop system to a closed loop system based on the subthalamic beta power. So I will have an example later on that. And just very briefly, and just actually for completeness, the stimulation protocols for epilepsy treatment are vagus nerve stimulation and responsive neurostimulation. So they are targeting to maybe like either suppressing seizures by detecting their onset and stimulating into the region with a setting which can suppress the seizure, or just diminishing the symptoms from epilepsy in general. So this was kind of a wrap-up of the clinical field and all the applications. So let's go to more advanced and more research-related scenarios. Here you can see a complete multipurpose brain stimulation research setup. So it basically includes everything you need, and in terms of hardware and software, to create sophisticated and versatile open loop and closed loop brain stimulation setups. We have a stimulator, we have an amplifier, and we have a switching unit, and they're connected together where the electrodes are connected to the switching unit. There is an electrode input to the switching unit, and these signals are either forwarded to the amplifier for recording purposes, or they are switched to the stimulator for stimulation purposes. All three devices are controlled by a PC, and this can be done in real time. So it allows us to stimulate, to sense, and to switch at the very same time. We can do it either open loop or closed loop, so we can use inputs data recordings from the amplifier, process it, and generate triggers or switching commands from the recorded data in real time. We can either use software triggers, so trigger by the control PC, or we can use hardware triggers, which is this kind of dark orange arrow here. So it's possible to connect the stimulator physically with a trigger cable to the switching unit, and then we can, in a very, very fast manner and in a very, kind of in high-speed protocol, we can trigger the switching unit by the stimulator and stimulate different areas up to a frequency of 100 hertz. We can either use adaptive settings, so during while the whole procedure is online, while the model is running, we can change the settings, and we can, as I already said, we can do real-time processing, and the software framework I will talk about in a minute also allows us to do convenient rapid prototyping. I will go through the hardware now a little bit more in detail. Let's start with the stimulator. It's the g.Estim Pro cortical stimulator. It's a medical device, so it's CE certified and also approved by FDA. It has a built-in self-test and some safety features, which basically makes sure that you're not stimulating beyond the limits which are healthy for the patient. You can either use it or control it with the software, but you can also use it in handheld mode, but also with a foot switch safety control connected. In terms of amplitude, we can go from 0.2 to 50 milliamps, where ramping is possible. So we can configure ramps over time. We can stimulate between 2 and 200 hertz for clinical purposes, but we can even stimulate up to 500 hertz for research purposes. The pulses delivered are rectangular, and they can have a duration from 100 microseconds to 1 millisecond. We can use either monophasic or biphasic pulses, or and also configure the stimulator such that it alternates the pulse sequence in terms of the sign. For clinical purposes, the standalone graphical user interface is mainly used. However, we also have a Simulink integration for closed loop systems. Let me show you a video which hopefully works very briefly. How the standalone GUI is working. So when you start the application, then you have this window which connects to the Estim Pro, and it's doing a self-test. So here the window is green, and it tells you everything is okay. And then you can go into either basic, handheld, or advanced mode. And for this example, we're just going into the basic mode. Enter some data to make sure everything is on record. Next, we have the electrode specification window, which where you have to enter your electrode data to make sure that the stimulator is not stimulating beyond the safe limits. And now we are in the main window. We can change the phase duration, so the duration of the pulse. We can change the amplitude. We can change the pulse rate. So here we have 50 Hertz. And then we have to activate the switch, the stimulator. And we have always to watch the electrode tissue impedance. So when we are when the stimulator is active, then the impedance can be continuously monitored. And once the impedance is low, for example, because the probe is touching the tissue, then we can stimulate. So I've missed that. So here, when we press stimulate, then you can see that the stimulator is active, the sequence is running. You can see the delivered current here and also the measured voltage at the same time. So this is basically it. It's, as I said, an open loop manual thing to do. So mainly for example, for ECS. All right. Yeah. Now, as I said, we also have an Simulink integration for the Estim Pro, which is shown here. We have a Simulink block. And when we double click this block, we have this mask with all the parameters we want to change. It's worthwhile mentioning that we can change the parameters, most of the parameters, while the model is running. So we don't have to stop the model, change the settings and start again. No, it can be done online. And this is what I meant with adaptive parameters previously. We can, for example, change the phase duration and the phase amplitude with these sliders here, but it doesn't mean that we cannot use any arbitrary input here to control the stimulator. We also have some output here, but you will see it later in the live demo a bit more in the real world context. Also this window here, I will show later more in detail. Now we have the amplifier, the g.Hiamp. It's probably the most, it's our flagship product, I would say. It's a very high quality invasive or non-invasive biosignal amplifier. It's a medical device, CE certified and FDA approved, at an input range of 340 millivolts at 24 bits. So we get the resolution of about 85, 86 nanovolts. We can sample up to 38.4 kilohertz. Also very important, especially for high-speed closed loop systems, we have synchronized digital input. So yeah, we can, for example, record any kind of sensors which give you a digital output. For example, yeah, this way we can synchronize visual stimuli, for example, with the data. The data is transmitted via USB to the PC. We have several headboxes, most importantly distinguished between active and passive headboxes, where stimulation in our context, of course, can only be done via passive headboxes. Yeah, we can record any kind of biosignals and sensors. And also the Hiamp has a Simulink integration for real-time data acquisition. Now, as I said, the most recent product we have is the switching unit. It's a programmable switching matrix where we have an electrode headbox input down here. You can see, so you connect, as you would connect to the g.Hiamp, you just connect the electrodes here to the switching unit. We have two output sockets. One goes to the g.Hiamp, so here on top, and one is for a third-party clinical monitoring system. And the switching unit allows us to configure stimulation channels up to 16 electrodes for plus and minus at the very same time. And we can record between or during stimulation. We have a graphical user interface and closed loop integration for MATLAB and Simulink. A little bit more detailed specifications are that we have hardware triggers. So as I told you already, on the back of the switching unit, we have a connector where a trigger signal can be received, and this way the switching process can be triggered, but we can also trigger it with software commands. We can switch up to 100 Hertz, and we can also select explicit ground channels, and here also up to 16 channels. Also, maybe interesting for people who are doing spike recording or other kinds of deep brain recordings or single unit recordings, we have a selectable audio out channel to allow auditory inspection of the signal. It has an integrated self-test, and it's also possible to do impedance measurement in combination with the g.Hiamp. So at this moment, we are in the very late prototype stage. So we have a functional unit here, which is about being type tested in the next couple of weeks. So we expect the research version to be available later this year. And once we have the research version available, we are, as soon as possible, going into the clinical certification process. And it will be distributed in variants of 64, 144, and 256 channels. So a very brief look on the graphical user interface of the switching unit is, it's actually very simple. You can select the electrodes here in groups of 64 channels. You can select positive, negative stimulation channel. You can select the audio out channel. You can select the ground. You can perform the impedance check, and you can activate the switching unit. So here, this is all very manual, and it's for the clinically certified version. So of course you cannot do everything what's possible with the switching unit, but you can do everything what is safe with the switching unit. If you want to go beyond it and do some research protocols, you have to go into Simulink, where you can see the Simulink block and the mask here. So here we have, as an input signal to the Simulink block, Stim plus and Stim minus channels. So they come as vectors of 16 values, and always when a value is not 0, this is interpreted as a stimulation channel. So at the very same time a change is received here, the switching unit is configured according to the input, and when an enable trigger is coming here to the switching unit is activated. So this is a software trigger, and we know when, also from the software, we know when the API calls are finished. And once everything is done software side, we issue an active, a rising edge at the active output here. If you even want to go beyond that, because this doesn't even allow to use the whole set of functions, you can use the MATLAB API, where you can see exemplary, or the API calls here. And basically, what is the main benefit here, or what is like the features you cannot use with the other versions or with the other variants, is that you can set stimulation sequences. So you can up to 64 elements. You can configure the switching unit such that it can iterate through a set of stimulation electrodes. With each trigger, it advances in this list, and this way you can pre-configure defined stimulation sequences. Of course, this is only dedicated and available for applications in the research field. So I've talked a little bit about Simulink blocks, and this is not a coincidence, because we at g.Tec, we have a very large library of Simulink high-speed processing blocks. It's called g.HIsys. And here, basically, everything is contained. It has many toolboxes, and it's not only about controlling our devices we have in real time, but it also contains a lot of very basic building blocks, such that you can easily prototype your own real-time experimental setup. Good. Now we come to the third part. Let me have a look. So we have about 20 minutes left. Maybe therefore we can skip this video, because Christoph has already shown it. It's an example, a typical example of open loop neuromodulation, where the temporal base, the phase selective, and the color preferred region are stimulated, and the patient, depending on the stimulation, has according symptoms and impressions and sensations. Something what has not been shown before is an example for deep brain stimulation, not only deep brain stimulation, but also single unit spike recording. What we have here, so this is a typical Simulink model. What we have here is a data source which provides us the data. Usually the g.HIm block is used, but this model was created from already recorded data. And then this data is recorded from single units, so from these very, very tiny electrodes, which record almost single neuronal pathways. It's split into single unit data and local field potential data, which has a larger electrode surface, and this way has just a different signal characteristics. So in the single unit processing example, we can go for spike detection and recording, and in the local field processing part here, we can implement adaptive deep brain stimulation. So I have two videos here. The first one is about the single unit processing. First, so the model is running, the data is retrieved from the data source, and here you can see in the G-scope the data. And this is a special scope. You can select a threshold based on the observed data. So here we have set 540 microvolts as a threshold, and this threshold is used to trigger the spike detector, and it's already running here. So this scope here visualizes the spikes, and at the same time the spikes are also counted. So this is a very basic example how you can do single unit spike recording and processing. Maybe more important in the brain stimulation context is the adaptive deep brain stimulation example. Okay, next slide. Yep. So here I have already mentioned that it's possible to link or to associate the extent of tremor or of motor dysfunction with the power in the beta band in subthalamic regions. So what we have to do here is actually quite easy. We are processing the data accordingly such that we end up with data from the beta band, and then we are filtering it and thresholding it, and every time the threshold is exceeded, we are triggering a stimulation. So this is a typical example of a closed loop brain stimulation system. Here you can see the video. It's the very same Simulink model as discussed before, but we're just observing the second block now. The data, first the stimulator has to be activated. So this is also a good example that shows you that we can operate the stimulator via the standalone GUI and the Simulink block at the very same time. So there is no interference here, which is problematic. So the stimulator here has been activated already, and it kind of listens now for software triggers from the Simulink block. In the Simulink block, we have standard processing. Okay, yeah, maybe just to go here. We have local field processing filter, so we're filtering out the channels which are from the local field potential electrodes. We're downsampling, and then we're going into the band power. So this here, what we are seeing in a second, in this scope is the band power in the beta band. We just have to wait until it comes. And this scope also allows us thresholding. Yep, so here you can see the power in the beta band and the threshold, and every time the threshold is exceeded, a stimulation is triggered. So now I will continue, and I think the video is also a little bit in slow motion to keep track of what's going on. So every time here we have an accession of, or yeah, if the signal exceeds the threshold, then the stimulator is triggered. Okay. Wait for it. Yeah, now it's a bit slower. You can see it. All right. Okay. Here you can see we have a signal exceeded the threshold, and the stimulator was triggered immediately. So this is a typical example of an adaptive deep brain stimulation framework. Okay, I don't want to waste so much time with that because now we are coming to a live demo, which is actually exactly the same setup I have described on the previous slides, which kind of shows you the most comprehensive stimulation framework we have available. And I hope it's possible to take the webcam now to show you this setup, because looking at pictures is nice, but looking at real setups is even better. So here, yep, I tried to get the focus. Let me just make this a little bit larger. Oh yeah, I have to share. I'm sorry, I have to stop screen sharing as well. Then you can see it. Yeah, perfect. So here you can see, actually it's mirrored. Anyhow, you can see the stimulator here. We have the foot switch connected, which is the safety feature, and it has always been to be pressed, so I fixed it with the tape. Never do this in a real scenario, please. It's just for demo purposes. The stimulator is connected to the switching unit, which you can see here. The switching unit receives signals from the electrodes, which I'll show in a second, and it also provides it forwards the signals to the g.Hiamp, which is located on top here. What the configuration here in terms of electrodes is the following. I have two signal generators here, which create 10 Hertz sine waves at the specific amplitude. And they are recorded at channels 17, 18. I've just selected arbitrary ones. And these channels are going to be used as the data we are processing and we are deriving our stimulation triggers from. At the very same time, we are recording data from some electrodes placed in saline, so it's just saltwater liquid. It's 4 electrodes here. And the idea of this experiment is that we are observing here the data from the signal generators, and once they exceed a certain power threshold, we are switching, depending on which channel is exceeding the threshold, we are switching either these two channels or the other 2 channels to the stimulator via the switching unit, and then we are stimulating into that. So I hope this was mostly clear. And now I will switch back to screen sharing. So how much time do we have left? Oh, very good. Screen sharing here. Yeah, actually we can go into the Simulink model. Here I have the Simulink model already opened. I have turned on the amplifiers, everything is set up. Here, the idea is we get the data from the g.Hiamp block. So we double click, and yeah, when screen sharing is active, it's always a bit slower, but usually the Hiamp configuration window should pop up. Just give me a second. Yep, here it is. Here in this window, I can configure the Hiamp. For example, I can choose the sampling rate up to 38 kilohertz, but here we choose 4.8 kilohertz. We can select the channels to record. Here I chose 17 and 18 for the signal generators, and down there 33 to 36 for the electrodes in the saline. And what I have also done here, because we are not recording real data, so it's just noise. And unfortunately, this also means that we have large line noise interference. To decrease this a little bit, and actually to also show a nice feature of Hiamp, is I'm creating a bipolar source derivation here. So channel 34 is recorded with respect to channel 33. So what we are getting here is actually the difference between those 2 channels. Good, so this is everything. We have 6 channels. What is also important is we have a trigger channel. So this is what I mentioned earlier. We have, in this case, the stimulator, the digital output of the stimulator is connected to this trigger input of the Hiamp, such that we can also see and observe when the stimulation was triggered. So this is also important. Now we have some, in this model, unbuffer and data conversion step is mandatory here. We go into basic signal preprocessing step which is, yeah, it's just not really worth mentioning it. It's not really doing anything. Then more importantly, we are deriving the stimulation channels here. So this is the main IP of this model and the main field where you're gonna experiment in. Here, I have the EG data coming in, trigger processing. So I'm a thresholding. It's, you know, it's all standard Simulink basic blocks. I'm thresholding, and then I create a selector. So based on which channel is exceeding the power threshold, I'm forwarding the index, either 1 or 2, or I'm forwarding just the active output trigger here. So the index goes into a selector, which selects the channels to be switched here, and output is then a stim plus and a stim minus data, which is then stim plus and stim minus, which is fed into the switching unit Simulink block. So now here we are at the switching unit. Let's double click it. What we have to do here is we have to perform a self-test before we can use it. So let me just switch it off and on again to make sure everything is okay. Okay, once more. Yeah, so now it's performing its self-test. It takes a little bit, 10 seconds roughly. It really switches through all the channels and makes sure everything is correct. And once the self-test is completed and successfully done, then the mask is shown. And the mask here provides us with the possibility to choose the ground channels, which we don't use now, and to provide the audio out channel index, which we just set to 50. Yep. Then we go into the g.Estim Pro block. Here for the first run, I will disconnect it to just show the switching process. But in the g.Estim Pro block, you double click, you end up with the mask here. You also have to perform a self-test every time you freshly connect a new Estim Pro. So it's not necessary all the time you're starting a model again. Okay, so here I have set 1 milliampere as phase amplitude and 100 microseconds for phase duration for now. So let us run the model now and hope everything will work. Okay, perfect. So what we see here are the first 2 channels. These are the signal generators. So you can see that once I will start one of them, you can see the oscillation coming here. And I will not go further now because I will explain the other channels. The other channels, channel 3 and channel 4, are the electrodes which are actually recorded. So these are the bipolar derivations, source derivated 34 minus 33 and 36 minus 35 here. So nothing is happening here, it's just plain noise. And down there, you can see the trigger channels. So I have also forwarded the trigger, software trigger into the datascope, and I have forwarded the active output trigger into the datascope. So let me increase now the signal. Let's do it a few times. And you can see here that because I have switched the second one, the first one, and it was, and here you can see the typical switching artifact from the switching unit. So channel 4 is not touched at all, but channel 3 is now switched accordingly. We can also do this with the other channel. So here I will use the second channel now. And you can see here that the second channel is switched and the first one is untouched. All right. What is also important to see is that down there, the triggers, so channel 6 is the software trigger derived from the data. And channel 7 is the software active flag from the Simulink block. So you can see here that this is really a fast reaction we get from the switching unit. All right. We have quantified it, and it's really below 30-40 milliseconds. So this is for a software trigger extremely fast. Now let's take the stimulator also into account. So while the model is running, I connect the stimulator now. And let's go back to the scope. So here, yep. So in channel 5, you can now see an additional trigger signal. So this is the response from the stimulator. And you can also see here the stimulation artifacts on the channel which is still connected. So this is, kind of a dry example with synthetic data, but it gives you a clue what you can do in real scenarios. So we can also, for example, go to here, and let's increase the current and the phase amplitude. And I guess the stimulation artifact should be much larger now. Yeah, you can see it's even visible here on the input channel because we are stimulating with so much current now. All right. So let me have a look at the clock. So 5 minutes are left. I think this is a good place to stop, and I guess there are also some questions. Christoph has maybe answered them already, but thanks for your attention, and yeah, please go ahead.
So I left some questions for you. Just please open the question and answer tab, and then you can just see 4 questions. Just start on top.
Okay.
So from Steve Potter, there's the first one. g.Estim Pro, what is the minimum latency for doing closed loop stimulation?
Sorry, the minimum, let me open the, seems like I'm not able to open it, but maybe I go to your window. Time of, so with g.Estim Pro, what is the minimum latency for doing closed loop stimulation time after event detected that the stimulus pulse can be delivered? And what is the jitter on that? Requires real-time operating system on PC. So depending regarding real-time operating system, we all use Windows. So as you all know, it's really not dedicated to do real-time operations in specific. Linux would be much better. So on Windows, it's really good to do that. And the minimum latency from a trigger is in the millisecond range, so it's about 2 to 3 milliseconds, and the jitter is very low. But we can give you more detailed answers on that. Can the g.Estim Pro do high-frequency stimulation? Yes, with the recently released software, we can go up to 500 Hertz for research purposes. How much freedom do you have to modify the stimulus? Pulse width, pulse rate, pulse shape, amplitude modulation of high-rate pulse trains. So it depends what you mean to modify the stimulus. So if we are below 200 Hertz, then we can adaptively modulate the parameters with the Simulink block. So there is no issue at all. What there is, of course, some processing time for the software to communicate it to the stimulator. Could we use ECoG for activities such as seizure caused by electrical cortical stimulation? You mean seizure detection? Yes, that's possible. And actually, it's also done. So when you this is also one reason why during ECS you should monitor the ECoG, and you can, for example, also look for fast ripples in the high gamma range, which tells you about a seizure onset. So actually, the ECoG is extremely valuable for that. But make sure that you have the correct coverage. So, for example, the hippocampus or the hippocampal gyrus is known as a center for epilepsy in many cases. So you should probably also have some coverage there. Good, thank you.